So hello everyone again. Welcome to the seminar. So today we've got Valentina De Romeri from the University of Valencia. So Valentina did her PhD in Valencia and the University of Turin before having positions at the CNRS and the IFT in Madrid, before moving back to Valencia, where she now has a position there. So Valentina is an expert on various things from neutrino physics to dark matter physics. She's also a member of the DUNE collaboration, which is a very exciting upcoming neutrino observatory. So it's great to have Valentina here to tell us all about dark matter physics and neutrino physics in experiments. So thank you, and take it away.
Okay, thank you very much for the introduction and for the invitation to give this seminar here. Well, I would have loved to visit your group in person, but okay, let's hope there will be a chance in the future. So in this seminar, I would like to discuss how we can probe new physics with both neutrino and dark matter experiments. And this presentation is based on these two works, which I've done recently in collaboration with Pablo Martinez Mirave, Mariam Tortola, Diego Aristizábal, Luis Flores, and Dimitris Papoulias. Okay, so this is the outline of the talk. I will start with a very brief introduction about physics beyond the standard model. And then I will separate the talk in two parts. In the first part, I will discuss the impact of coherent measurements of the coherent elastic neutrino-nucleus scattering cross-section and other uncertainties related to other quantities on the neutrino floor. So I will present different analyses that we did, a data-driven analysis and other analysis where we consider the impact of uncertainties, for instance, from the nuclear form factor or the weak mixing angle on the discovery limits for WIMPs. In the second part of the talk, instead, I would like to discuss something different, that is the possibility of detecting dark matter in the form of primordial black hole with future neutrino experiments. So I will first discuss how neutrinos can be produced from primordial black hole evaporation, and then I will present sensitivities for the future experiments DUNE and THEIA. Well, we all know that the standard model is a very nice theory that can explain most of the experimental results that we have nowadays. However, there remain some theoretical and observational issues to be addressed. Among these, an explanation to neutrino oscillations and masses and to the nature of their matter. In particular, neutrino oscillations are considered as the first laboratory evidence for new physics, and they are considered as a hint for the standard model to be extended or at least embedded in a larger framework. So at this scope, many candidate new physics models have been introduced in the literature. They introduce some new physics at different energy scales, and this new physics is currently actively searched for in many fronts at high energy colliders, at high intensity facilities, via cosmological and astroparticle physics probes, and with neutrino experiments. In this talk, I'm particularly interested in the latter two possibilities and on the complementarity among these different facilities in shedding light on new physics beyond the standard model. So let me start with the first part of this talk about the impact of coherent measurements, cross-section uncertainties, and new interactions on the neutrino floor. Okay, we know that there is overwhelming evidence for the existence of dark matter, and we have inferred its existence from different observations on different cosmological scales. So we have inferred the content of the universe. Here it is shown in terms of paella, and we know that the part of it is made of dark matter. We still don't know what is the nature of dark matter, but we know that it has to fulfill with some properties. It has to be non-baryonic, collisionless, stable on cosmological scales, or at least very long-lived, neutral, massive, cold, or at least warm in order to explain structure formation, and of course not in conflict or excluded by dark matter experiments and cosmological data. So since none of the particles of the standard model can explain it, many candidates have been introduced, in particular in the form of particles whose masses and cross-section interaction can span over many orders of magnitude. In this first part of the talk, I will be interested in WIMPs. because WIMPs, and in general, if their matter are made of particles like WIMPs that interact among themselves and with standard model particles, we may hope to detect it. So different strategies have been envisaged at this scope, in particular direct detection and indirect detection. Here, in this first part of the talk, I'm interested in the direct detection, which is the technique that looks for the energy deposited within a detector by the dark matter nuclei scattering. So I guess we are all used now to see these kind of plots, which summarize the current status of direct detection searches. So all these contour lines represent the current limits set by different direct detection experiments. On the WIMP parameter space in terms of cross-section and mass. So these experiments are improving in sensitivity and right now are already exploring a large region of the parameter space. But as we can see in this plot, there is this orange dashed contour, which refers to the neutrino floor, the so-called neutrino floor, which is seen somehow as the limit below which these experiments would not be able to disentangle between a WIMP signal and a neutrino signal. Indeed, we expect these near future multi-ton dark matter experiments to be sensitive also to the fluxes of astrophysical neutrinos from the sun, the atmosphere, and from supernovae. These are the fluxes of astrophysical neutrinos that we expect can be visible within these experiments. So below, let's say 10 MeV, solar neutrinos are the most relevant ones, in particular those from boron 8, but also other fluxes from beryllium-7 and the others. Around the 10 MeV, also we expect quite a sizable flux from a diffuse supernova neutrino background, which is a cumulative flux of neutrinos produced from a distant core collapsed supernova. Even if these neutrinos have not been observed yet, we do expect this signal to be visible in near future experiment. And at higher energies, also atmospheric neutrinos from the scattering of high energy cosmic rays in the atmosphere would play a relevant role and would constitute a background for dark matter direct detection searches. These astrophysical neutrinos would induce a signal within these experiments via this process, which is the coherent elastic Neutrino-Nucleus scattering, also called as sevens. This is a neutral current process in which the neutrino scatters off a nucleus via the exchange of a Z boson, and the neutrino sees the nucleus as a whole. So for this process to occur, the neutrino energy has to be such that the nucleon amplitudes sum up coherently. So this means that there is an upper limit on the energy of the incoming neutrino of around 100 MeV for typical medium-sized nuclei. And this leads to a cross-section enhancement. So the total sevens cross-section turns out to scale with the number of neutron squares, and it can be quite large. For instance, few orders of magnitude larger than the inverse beta decay process, which was first used to observe neutrinos. Despite the magnitude of this cross-section, so this process was first proposed theoretical more than 40 years ago, but it had not been observed during many decades because this process produces a very tiny recoil energy. So it's very complicated to observe this signal. However, the improvement in detector technologies, also thanks to the technology of direct detection experiments, which share the same, let's say, technologies indeed, so have allowed to observe this process for the first time in 2017 by the Coherent experiment. So this process has a well-calculable cross-section in the standard model. In principle, it receives two contributions, an axial one, which, however, it's small for most nuclei because it's spin-dependent. So the relevant contribution that dominates is the vector one. And these expressions gives the differential cross-section for the sevens process. So we see the dependence on this weak nuclear charge, which encodes the typical n-squared dependence of the process. And also this process depends on the nuclear form factor, which approximates 1 in the case of full coherence. This plot shows the typical n-square dependence, as I was saying, of the cross-section for different neutrino fluxes and different target materials. So if we go back to the astrophysical neutrinos that we discussed before, so we expect these neutrinos to produce a signal in these direct detection experiments. And for instance, this plot shows the expected recoil rates on nuclei of xenon for solar neutrinos, atmospheric neutrinos, and the SMB. So it's quite interesting to observe, for instance, here that some of these fluxes, it's quite clear in the case of the flux from boron 8, could mimic quite well the signal expected from a WIMP, for instance, in this case, with a mass of around 6 GeV and a cross-section of around 10 to the minus 45 centimeters square. So this tells us indeed that these neutrino backgrounds will induce a 7 signal in these experiments and produce nuclear recoil spectra, which can have strong degeneracies with those expected from WIMP interactions. So increasing the exposure of forthcoming multi-ton experiments does not imply a linear improvement of sensitivities, but rather a saturation of the discovery limits, which is what we typically refer to as a neutrino floor. So these neutrino floors actually can vary depending on different factors, concerning the WIMP rates on astrophysical uncertainties, of course, whereas concerning the seventh rates, they will depend on nuclear physics uncertainties, on the neutrino flux uncertainties, and on the possible existence of new physics interactions. These neutrinos floors could in principle be overcome with measurements, for instance, of the WIMP and neutrino recoil spectral tails with directionality, with the use of different target materials. But in any case, it seems clear that in order to correctly interpret the results from near future experiments, we need to fully understand where these neutrino floors lie for each experiment and which are the uncertainties that play a relevant role in computing these limits. So this is what we were interested in particular on the seventh contribution. So we wanted to compute the WIMP discovery limits. Let me define what we mean by a discovery limit. So the discovery limit is meant as the smallest WIMP cross-section for which a given experiment has 90% probability of detecting a WIMP signal at 3 sigma level or more. So to compute this, we followed a standard procedure, which is to adopt a standard profile likelihood ratio as a test statistic, where we define the likelihood function in this way, where P and G are Poisson and Gaussian function distribution probabilities. So we assume the observed number of events to follow a Poissonian statistics, whereas the nuisance parameters related to different uncertainties that I will discuss soon, or with the neutrino fluxes, are assumed to follow Gaussian statistics. Then the profile likelihood ratio corresponds to a test statistic against the null hypothesis, where you assume only the background from 7 neutrino events, versus the alternative hypothesis, where instead we assume the sum of both the WIMP signal and the 7th background. In general, both the calculation of the signal and of the background events can involve nuisance parameters. We were interested in the latter, in the uncertainties affected the background. And we decided to consider 2 different cases. In the first case, we assume we consider WIMP searches in the presence of a standard neutrino background, with uncertainties on the normalization of neutrino fluxes combined with other uncertainties, either the uncertainty on the 7th cross-section or on the neutron mean square radius, or uncertainties related to a possible variation at low energy of the weak mixing angle. Then in the second case, instead, we performed a different set of analysis where instead we consider WIMP searches in the presence of non-standard neutrino background. So either the existence of a new interaction mediated either via a light vector or a light scalar, or the possible existence of neutrino magnetic moments. Let me start with the first one, so the so-called data-driven analysis. So in this case, what we wanted to do was to exploit the information of coherent measurements of this seventh process. So we wanted to use the measured seventh cross-section with its uncertainty. With this approach, we mean to encode all possible uncertainties that the cross-section can involve independently of assumptions. So this would be a kind of model-independent analysis. So to do so, we had to extract the seventh cross-section from coherent cesium iodine and liquid argon sets of data. We extracted the central values together with their standard deviations. So what we did was to weigh the theoretical standard model value of the cross-section by a multiplicative factor. And we performed the chi-square analysis to fit this multiplicative factor in each energy recoil bin. So this plot shows the values that we have extracted for this multiplicative factor for each recoil energy bin for the set of data of cesium iodine and liquid argon. So with this information, we computed the WIMP discovery limits. And we computed them for future xenon and argon experiments. So in the case of the xenon experiments, we used the data from the cesium iodine set, since the nucleids share almost the same properties, same mass and atomic number, or very similar. Whereas for the argon, of course, we use the data set from liquid argon. So in these plots, the solid contours, colored contours, correspond to the standard model expectation. In this case, it's the case where we fix the value of the seventh cross-section to the standard model one, whereas the dashed contours are the discovery limits that we obtain when we allow for this variation of the seventh cross-section within the range of that we have obtained of this multiplicative factor. And the different colors correspond to different exposures. So we see from the left plot that in the case of the analysis with the cesium iodine data, compared with the standard model expectation, the WIMP discovery limits improve. And this is because if we go back one moment to the previous plot, here we see that the central values that we have obtained are almost in all bins, lie almost in all bins below the standard model value. So this means that the measured cross-section is smaller than the standard model expectation and thus resulting in a background depletion. And that's why the discovery limits improve. Of course, the effect is more visible with larger exposures. In the case of liquid argon data, instead, the situation is the opposite, because again, if we have a look at this plot, the situation is different. So the central values are slightly larger than the standard model one. Of course, the effect is not large, but here we get that the discovery limits are slightly worse when we allow for these uncertainties on the measured seventh cross-section. The second analysis from the first set that we did is also to consider the impact of nuclear form factor uncertainties on these WIMP discovery limits. So neutron distributions are not well measured compared to the proton ones, and in principle there can be differences between the proton and neutron distributions, which are actually expected to be substantial for neutron-rich nuclei. So this difference can have an impact on the values of the nuclear form factor and hence also on the WIMP discovery limits. So we adopted the Helm parametrization for both the proton and neutron nuclear form factors. We fixed the proton mean square radius and we allowed instead for a 10% variation of the neutron mean square radius. So again, this plot shows the results expected in this case. First of all, we see that at low WIMP masses, the zero momentum transfer limit is a very good approximation. So we see no effect because basically the form factor are well approximated by 1. Where we see some difference, some effect is where, let's say, the boronate flux is sizable, so where we have a bit more statistics. And the effect of this variation on the neutron mean square radius is that when we increase this value, the nuclear size increase. So the loss of coherence happens for a smaller Q. Also, I mean, when at heavier masses, instead we don't have a large effect anymore. Also, for a combination of effects, first of all, the effect in itself is not large. The statistic is also lower here, and as this radius increases, both the neutrino background and the WIMP event rate are actually slightly suppressed. So overall, the effect of this uncertainty on the nuclear form factor is not large on the WIMP discovery limits. The third case that we considered is the impact of uncertainties on the weak mixing angle. So these are expected to be relevant at low WIMP masses, where we have large fluxes from solar neutrinos. So we calculated the WIMP discovery limits, combining uncertainties on the neutrino fluxes and on the weak mixing angles. Also here we assumed a 10% of variation. And also in this case, we see that the largest effect is visible at low masses, where these solar neutrino fluxes are relevant. In this case, the fact is that when the weak mixing angle increases, the coherent weak charge becomes more negative. So when we increase the weak mixing angle, for instance, by 10%, we get an increasing of this charge of around 12%. And this leads to an enhancement of the 7th background and therefore to an worsening of the discovery limits. Again, the effect is quite small and only visible in this low mass region. Then we considered, as I said before, a different set of analyses where we assume the possibility of the existence of some new physics interactions. The first one that we were interested in is the case of light vector mediator. So in this case, the coherent weak charge is modified in this way. We have this extra term, which depends on the mass of this light vector mediator and on this product of couplings, which refer to the coupling of the vector with the nucleus and with the neutrinos. We fix this product to the maximum allowed value according to coherent data, because we wanted to maximize the effect on the WIMP discovery limits. And in this case, the only nuisance parameters that we consider are those associated with the neutrino fluxes. So the result is shown in this plot. We see that the effect is here quite pronounced, it's quite large. And it's in particular visible also at low masses below, let's say, 10 GeV. This is because at low momentum transfer, the new contribution is enhanced, and so the neutrino background actually increases quite a lot, and therefore the WIMP discovery limits get much worse. At higher masses, the situation is inverted because, well, the standard model coherent weak charge is negative, while the new contribution is positive. So what happens is that at larger momentum transfer, the new contribution becomes less important, and it interferes destructively with the standard model term. So that's why here actually the discovery limits slightly improve. The second case of new interactions that we considered is that of a light scalar mediator. Here in this case, the 7th cross-section is given by the sum of the standard model term plus this new term, where again we have, in this case, we have a scalar charge, let's say, which also depends on the mass of the light scalar and on a product of coupling, which again we set, we fix to their maximum allowed value. Also in this case, we get quite a sizable effect, quite a sizable difference on the WIMP discovery limits, although less important compared to the vector case. Again, the largest effect is for masses below 10 GeV, because this scalar contribution peaks towards the low momentum transfer region, which corresponds to the low WIMP mass region. And therefore there it enhances the background and worsens the discovery limit. At higher masses, it also continues to slightly worsen the discovery limits, but it then approximates to the standard model contour. Because in this case, the destructive interference is not possible because there is a chirality flip. So it still adds, this contribution still adds to the standard model, but if it's at large momentum transfer, it's very small, and therefore the effect is almost negligible. Finally, the last analysis that we did in the case of these new interactions or new properties of neutrinos is the case of neutrino magnetic moments and transitions. So in this case, the seventh cross-section is increased by this new term, which depends on this parameter, mu effective, which is an effective parameter which encodes these neutrino magnetic and electric dipole moments. Also in this case, we fix the value of this mu effective to let's say the largest value currently allowed by both gamma and xenon one-ton analysis. And okay, the main feature here is to produce a spectral distortion from this process. So this plot shows the effect on the WIMP discovery limits. Also in this case, the largest effect is visible at low WIMP masses below, let's say, 0.2 GeV. And again, the effect is to worsen the discovery limits because of background enhancement. At higher masses, or also in the region of large transfer momentum, instead the effect becomes almost negligible, and therefore we cannot see any difference on the WIMP discovery limits compared to the standard model case. So let me summarize this first part of the talk. So in this first part of the talk, we were interested in understanding how WIMP discovery limits would vary depending on different uncertainties. And actually the motivation behind this is that these searches for WIMPs using forthcoming multi-ton detectors will require a precise understanding of WIMP discovery limits in order to fully understand and to extract the most appropriate information from data. So we have reconsidered possible variation of the neutrino floor. In particular, we were interested in exploiting the recent results, the recent measurements of the seventh process by the Coherent collaboration. So we performed different analyses, a data-driven one, in which we have treated the seventh cross-section as a parameter, which is entirely determined by experimental data in order to be the most model independent as possible. And then we have performed other analyses where we allowed for uncertainties on the nuclear form factors, on possible fluctuations of the weak mixing angle at low energies, and finally also the existence of new interactions. So in this case, we performed some model-dependent analysis with the idea of illustrating the impact of new physics in the neutrino background on the discovery limits. Okay, so with this part, with this, I conclude the first part of the talk, and then now I would like to discuss in the second part something different, because now I was discussing how new physics or let's say neutrino physics can affect the search of dark matter with dark matter experiments. In this case, I would like to discuss how neutrino experiments could help in the search of dark matter, and in particular how we could search for dark matter in the form of primordial black holes with future neutrino experiments. So here I will not talk about WIMP, but about primordial black holes. So let me introduce primordial black hole dark matter. Primordial black holes are formed from the collapse of large inhomogeneities in the early universe before the BBN epoch. And actually, they constitute one of the earliest and most appealing dark matter candidates. So they have been studied during the last years in quite a lot of detail, and several constraints have been inferred on their parameter space. So this plot summarizes the current status of primordial black hole dark matter in terms of this parameter f, which is the fraction of dark matter. So if f is equal to 1, it means that the totality of dark matter can be made of primordial black holes. And this parameter is given in terms of the primordial black hole mass in solar masses or in grams. So we see that currently there is only one region, which is this window here, which is the so-called asteroid mass region, where these primordial black holes are completely allowed. Let's say they could constitute the totality of the dark matter. In the past, some constraints had been claimed to apply here from neutron stars and white dwarfs, so from spectral distortions of gamma ray bursts. But eventually they have been shown to be not robust, so at the moment no bounds apply here. However, we are more interested here in the light mass region below, let's say, 10 to the 17th or 10 to the 16 grams, because this is the region that we can probe with neutrino experiments. So if we zoom here and there, we can have a look in more detail at all the bounds that apply in this low mass region. And most of these bounds are obtained from evaporation constraints. Indeed, primordial black holes and in general black holes are thought to evaporate via Hawking radiation, emitting particles near their event horizons. So very light, non-rotating primordial black holes with masses below 5 times 10 to the 14 grams are expected to have completely evaporated by now, but heavier primordial black holes would survive until now, so they would constitute a good dark matter candidate, but still they would evaporate, producing fluxes of also standard model particles. So a large number of constraints have been derived on the abundance of these light primordial black holes with masses between 10 to the 15, 10 to the 17 grams from the non-observation of their evaporation products, namely photons and in particular gamma rays, but also electron positrons and neutrinos. Moreover, other constraints can apply in this mass region, from distortions of the CMB, for instance, or from the heating of neutral hydrogen or the heating of interstellar medium, but I will not discuss these in detail here. As I was saying, these primordial black holes, which can also be rotating, can also have a spin parameter, will emit particles following a black body-like distribution. To compute the spectra of emitted neutrinos from evaporation, we relied on a public tool, which is called Black Hawk, and we considered two contributions. The first one is the primary, which are the neutrinos, which are directly emitted in the evaporation of the primordial black hole. And the other one is the secondary contribution, which instead stems from the hadronization and subsequent decay of primary particles. Moreover, both primordial black holes in the galactic halo and outside will contribute to the differential neutrino flux from primordial black hole evaporation. So in the case of the galactic contribution, the differential neutrino flux is given by this expression. It will depend on the dark matter fraction, on the mass of the primordial black hole, on this spectrum of emitted neutrinos from evaporation, and on this other term, which is somehow an equivalent of a D term in the case of the decaying dark matter, which is basically the integral along the line of sight of of the dark matter density profile of the Milky Way. For the extragalaxy contribution, instead, we have to make an assumption, that is that the dark matter is distributed isotropically at sufficiently large scales. Then the extragalactic differential neutrino flux is estimated as the redshifted sum over all epochs of emission. Let's have a look at how the total differential neutrino flux from primordial black holes look like. Here we are assuming a monochromatic primordial black hole mass distribution and different spins. So this plot shows this differential flux expected for 3 different values of mass from 10 to the 15 to 10 to the 16 grams. And each of them for 3 different values of spin. The solid curve corresponds to the case of a non-rotating primordial black hole, whereas the dashed and the long dashed curves correspond respectively to a spin 0.5 and 0.9. So first of all, we observe that if we consider heavier primordial black holes, these lead to reduced fluxes shifted towards smaller neutrino energies. So this somehow also tells us that we have pragmatically an upper limit on the masses of primordial black holes that we can study with neutrino experiments. Because if we want to investigate primordial black holes with masses above 10 to the 16 grams, we would entering a region where we have very large backgrounds from solar neutrinos, from geoneutrinos, or from reactor neutrinos, depending on the experiment. Then we also see that some peculiar features appear for rapidly rotating primordial black holes with a spin parameter of 0.9. These peaks at high energies appear for the radiation of particles with higher angular momentum, which indeed lead to a substantial enhancement when the flux of the latter is aligned with the primordial black hole one. Then also some other consideration on these neutrinos from primordial black hole evaporation. So this primordial black hole evaporation rate depends on the total number of degrees of freedom of the emitted particles and on their masses. So first of all, we assume neutrinos to be massless, but this is a very good approximation because the non-zero masses would make a very small difference, as they would be relevant only at temperatures of the primordial black holes close to the neutrino mass. And also we assume them to be Majorana neutrinos. If we were to assume them to be Dirac, then we would get, let's say, around a factor of 2 of difference, as we can see in this plot, in the differential flux, close to the peak given from the primary galactic contribution. Also, another assumption that we did was not to include the effect of neutrino mixing in our analysis. This would be relevant only for secondary neutrinos, which stems from the decay of other particles. Still, we did the test and we tried to include it, and we saw that considering this neutrino mixing would reduce the total differential flux by less than 2% for the neutrino energies and primordial black hole masses that we were interested in. Another relevant comment is about the primordial black hole mass distribution. So all the plots that I showed until now were obtained assuming a monochromatic mass distribution, which is a good simplification to make calculation and also to compare with existing constraints in the literature. However, it's not very realistic because a large variety of formation mechanisms from inflations, for instance, predicts extended mass distribution for these primordial black holes. So something that is usually done for this phenomenological analysis is to consider a log normal distribution for the comoving number density, which is assumed to be, let's say, an approximation of these more realistic mass distributions. This is given by this expression here. So the relevant parameters here are the critical mass, which refer to the position of the peak, and the sigma, which refers to the width of the distribution. So these plots want to show how the differential flux is changed if we consider an extended mass distribution compared to a monochromatic one. We see that the main effect is that if you consider a distribution with a large width, for instance, sigma equal to 1, the typical peak from the galactic primary contribution is smoothed down, and also the flux is still relevant at higher energies. Okay, so we were interested in two future neutrino experiments. The first one is DUNE. The DUNE, this analysis could be done for exploiting the DUNE far detector, which would be mainly sensitive to the electron-neutrino component of this primordial black hole neutrino flux via the absorption of these neutrinos on nuclei of argon. In this analysis would have some backgrounds, solar neutrinos for energies below 16 MeV, and charged current atmospheric neutrinos for energies above, let's say, 30 MeV. We got rid of the first ones of the solar neutrinos, cutting our analysis more or less at this energy. We did include the atmospheric neutrino background, and also, even if it has not been observed yet, the diffuse supernova neutrino background would constitute a background for this analysis. And it's actually expected to be visible at DUNE. So we simulated it and included in the analysis as a background. This plot shows then the expected number of events as a function of the neutrino energies for DUNE, assuming 40 kiloton of fiducial volume, 10 years of data taking. And the different colored curves correspond to different primordial black hole masses, their matter fractions, spin parameters, and mass distributions. The second experiment that we considered is THEIA, which is a proposal for a water-based liquid scintillator. Here, the dominant reaction channel would be inverse beta decay, so somehow it would be complementary to DUNE, because THEIA would observe antineutrinos, whereas DUNE would observe neutrinos. Well, THEIA it's just a proposal, so it's not clear, not even where it could be located. But one proposal is that it would constitute an extra tank for the DUNE far detector. So that's why we were interested to include it in the analysis. For THEIA, we would have some extra backgrounds besides the solar neutrinos and the charged current atmospheric neutrinos. We would have also reactor neutrinos, depending on the location of the experiment, and neutral current high energy atmospheric neutrinos. We could also mimic the inverse beta decay signal. So we performed a statistical analysis assuming these least square functions, where we took into account, as I said, the different backgrounds in the case of DUNE, the SMB and the atmospheric charge current. And in the case of THEIA, also the SMB and atmospheric, charge current, and neutral current background too. So these are the results, the expected sensitivities that we obtained for DUNE in the parameter space of primordial black holes, so the dark matter fraction and the mass. So the left panel corresponds to the analysis performed assuming a monochromatic mass distribution. The right one, it's obtained assuming a log normal, so an extended mass distribution with 3 different values of width. In the case of the monochromatic distribution, instead, we allow for 3 different values of spin. So our sensitivities are these orange, red, and dark red contours, which we compare with the existing constraint using also neutrinos, so using super Kamiokande data, which is this gray shaded region. And we also compare with the future expected sensitivity at Juno, although at a different confidence level. Moreover, this yellow region is actually a sum of different constraints obtained using different cosmic messengers, in particular photons, but not only. So here they are shown in more detail. Probably the most robust among these is the one from the extragalactic gamma ray background. So just to give an idea of how our sensitivities would compare to these constraints, of course, are different messengers, as I was saying. So we are considering neutrinos, these are mostly photons, but just to get an idea. And well, all in all, I mean, DUNE could for sure improve the current sensitivity of super K, and actually would allow to reach quite low fractions of dark matter for primordial black holes with a mass of a few times 10 to the 15 grams. So the result could be quite competitive. For THEIA, the situation is quite similar. So we performed two different analyses because, as I said before, it's just a proposal. So it's not even clear what would be the mass, the volume of this experiment. So we considered two cases, one of 25 kiloton of volume. In that case, it would constitute this extra tank of in the DUNE cave, or the case of an independent experiment with 100 kiloton of volume. Also in this case, we see that THEIA could improve the existing limit from super K. For sure, in the case of the monochromatic distribution, in the case of the log normal, it would improve at least at low primordial black hole masses. And it would give, I mean, the sensitivity expected would be comparable to what is expected also at Juno. So I come here to the conclusions of this part, but also of the whole seminar. So in this second part of the seminar, we considered primordial black holes as a viable dark matter candidate, which we have seen have masses that can span over several orders of magnitude. We were mainly interested in light primordial black holes with masses in the range between 10 to the 15 and 10 to the 17 grams, because these could evaporate and produce sizable fluxes of MEV neutrinos via Hawking radiation. And we have explored the possibility of detecting these neutrinos with future neutrino experiments DUNE and THEIA. Our analysis showed that both DUNE and THEIA could improve existing bounds from super Kainokande and also allow to reach primordial black holes masses up to 5 times 10 to the 16 grams. So this analysis is meant to show that the next generation neutrino facilities could set competitive bounds on the primordial black hole parameter space, complementary to other limits from other cosmic messengers, in particular photons. And well, I think the thing that is interesting to highlight here is that, of course, the quest for primordial black hole dark matter and future neutrino experiments, it's not among the main objective of these experiments, but it could be easily included in their physics programs. In particular, leveraging existing supernova neutrino analysis. As we have seen, the expected fluxes would lie exactly in the same region of the SNB flux. So I think it would be interesting to include this somehow analysis in an easy way in the physics program of these future neutrino experiments. So with this, I conclude. I thank you for the attention, and if you have questions.
Thank you very much. That was really fascinating. Do we have any questions from anyone? Please just unmute yourself.
Actually, I have a question.
Sure.
So I don't know which exact version of Black Hawk you used. Maybe it's one of the newer versions. But did it have updated Pythia tables, or did you use just extrapolate from the Pythia tables for the secondary products? Because at least in the version of Black Hawk I have used, you can't do anything but extrapolate beneath 5 GeV, I think.
Yeah, you're right. We were using, so we did this analysis in last spring. So we didn't use the very last version of Black Hawk because it came out in July, I think, or August. So we used the version just before that, and we are aware of indeed of the uncertainties on the extrapolation. Indeed, it's extrapolating at low energies for the secondary, so we are aware of that, which indeed are quite relevant.
Yeah. Okay.
But I mean, still, let's say that the most relevant contribution, I would say, in the analysis comes from the peak of the galactic primary, because I mean, the secondary flux would be at lower energies, which most of the time we cut. So because we want to get rid. So at the end, it does not affect much the results, I would say.
Does it matter which halo model you use to model the galactic?
Of course, a bit it matters, but not so much. We tried with a core isothermal, and the change was quite small. Now I don't remember if it was like a factor of 2 or so, but it was not so relevant for sure. It's more relevant to change the primordial black hole mass distribution. That changes quite a lot.
Oh yeah, of course. Yeah.
What did you use? Sorry, as an NFW for the halo?
We used an NFW, yes.
Yeah. Anyone else want to ask something quickly? If not, I can go ahead. I have many questions. Let me just try and find one which is most relevant. Yeah, actually, the bit I kind of lost you was when you were talking about the neutrino oscillations, because you're considering just the charge current interactions from the PBH neutrinos in DUNE. But what do you assume about the flavor content? I mean, I don't know what the flavor content is that would be emitted by the primordial black hole in the first place, let alone the effect of neutrino oscillations as they propagate.
Yeah.
So what is going on there?
No, I mean, so from the evaporation, basically the neutrinos are emitted as mass eigenstates. So that's why actually the flavor is not relevant there. I mean, when I think it was here, probably, no, here, that we did not include the neutrino mixings. This would affect the secondaries, which instead are produced from the decay of the other particles. Yeah, I mean, the effect would not be large anyway. We tried, actually, we did a test. Would be larger if we were to consider, for instance, lighter masses or lower energies, lower neutrino energies. Then this effect could be more than 2%, like 10% or so. But in this, let's say, energy range and mass range that we were interested in, the effect is not large. And then, I mean, DUNE observe electron neutrinos, at least with this, the process that we considered, which is this absorption of nuclei of argon. It's electron neutrinos. So yeah. We considered we computed all the flavors and all the flavors and of neutrinos, but then we consider only the electron neutrino component for this analysis. For THEIA instead is the anti-neutrino component.
Yeah. And so what happens to the neutral current events? Are they just at lower energies?
Yeah, no, the cross section would be smaller. So we decided to consider this one because it's the one that leads to the largest signal. But of course, we could have other signatures also from neutral current. So,
because yeah, I noticed on the bottom plot there's like you have the atmospheric neutral current event. Is that just because the atmospheric neutrinos are at such high energies that they still generate neutral current, like sizable neutral current events?
Yeah, I mean, this is a background that can mimic this inverse beta decay. And therefore, that's why it's relevant here. Yeah.
So some people have to go. They're giving apologies. Maybe do we have any further questions? If not, I can just keep going. One thing. One thing I want to know, going back to the first part of the talk. So. Sure. The effect of this form factor looked relatively minor, but do you have any idea of, like, because I think do you ignore the axial vector terms in sevens here? Because I mean some xenon isotopes would have an axial vector contribution, right? Is it just that it's really, really small?
Yes, we assumed it to be small. Yes, we consider the main vector contribution.
I mean, do you have an idea of like how large? Because I mean, this is already kind of a relatively minor effect. I don't, because then there would be an uncertainty on the, because there'll be a different form factor presumably for the axial vector terms. So I wonder if that additional uncertainty would be relevant here. But I mean, I don't know. I have no idea of this relative sizes of the axial vector terms.
Yeah, I cannot estimate, so I don't know. I guess it would be probably even smaller. I mean, as the axial contribution would be smaller.
Yeah.
And this effect, it's not large, but really, I mean, we didn't consider that, so I cannot estimate.
And what else was I going to say? Oh yeah, so the yeah, another thing I didn't quite follow. So when you were doing the data-driven analysis for the based on the sevens cross-section measured by so if I'm right in thinking that so for the xenon one, you were considering the cesium iodide measurements. And then, so I think your claim was that when you use the measured cross-section, which is slightly lower than the standard model prediction, but then the standard model prediction in the usual case, you don't consider any uncertainties on the cross-section at all. So I'm surprised that you still end up being lower even when you include because it didn't look like it was significantly lower than the standard model cross-section, because the error bar still goes above the standard model prediction. So I'm just surprised that the difference is so large for that xenon case.
Yeah, that's true. But indeed, I mean, this was our interpretation of this result. I mean, we included indeed these uncertainties on the values of the cross-section. In the case of the standard model, we assume it to be, I mean, we computed it in the standard model without any uncertainty, no?
Yeah.
And for the measured one, we included indeed these central values with these error bars. And yeah, I mean, we get this effect. I mean, statistically, the number of events are smaller. I mean, from in the case of the measured seventh cross section. So that's why
it's like the number of events is small enough to make up for the fact that you've got this added uncertainty.
It seems so, yes.
Okay. Yeah, interesting. Okay, so before we go too far over time, I think if anyone has any final questions they want to shout out, just go ahead, but I don't think so. So